All right, so we finished case 1, and we are still working on the induction step. Now we're going to be doing the other case, that m is actually in the range of f. And remember, we've assumed that we have an injection f from n to n plus 1, and we're trying to prove that n is less than or equal to n plus 1. We want to somehow use our induction hypothesis, so in the back of our minds we're thinking, can we somehow get an injection from something to m? I say something, it doesn't have to be n because this is bound here by the universal. Okay, so case 2, m is in the range of f. How about I move case 1 out of the way here so we can see everything in one screen. All right, there we go. So case 2, case 1 is already done. Case 2, suppose that m is in the range of f. So let's go back to our picture. So we have our injection f from n to n plus 1. N consists of these things, 0 up through n minus 1, and m plus 1 consists of these things, 0 up through m. And now I'm assuming that m is definitely in the range of f. So I'm going to make this dotted line actually a solid line. So we definitely know that m comes from somewhere back here. There's some arrow going somewhere, I don't know where, that ends up at m. And all the other ones, I don't know. There's at least, or at most, one line, right? Either 0 or 1 edge leading up to the other ones. So what to do now? Remember, I want to use the induction hypothesis. I want to somehow reduce myself to the case where I have an injection to m rather than m plus 1, right? So how do I get an injection to m? Remember, m is, if I just scare quotes m minus 1 there, m would be this set, the set with these elements. That would be m, right? So having this arrow here is definitely an obstruction to cutting myself down to a situation where I have an injection to m. So right now I don't like that this arrow is there. So what to do? So now we're going to execute our plan from before. So we've got m is in the range of f, so it comes from somewhere, right? This arrow is coming from somewhere. I don't know where. Let's say it comes from k. So let me give the name k to whoever sits in the middle here and ends up going to m. And actually, let me expand this picture a little bit so that there's more room for things. Okay, I'm just going to make a new picture. So here's my picture of the set m plus 1. Here's my picture of the set n. I've got my mysterious bijection f, which takes in all of these arrows here and does some stuff to them, but I don't know what it does. But I am assuming I'm in a case where m arises as an output, so m comes from somewhere, and I've given name k to wherever m comes from. Like that. And all these other guys, they might have a preimage, they might come from somewhere, or they might not, right? So I'm using a dotted line for that. And there's never two lines coming in, so you couldn't have this because of the injectivity. Okay, so this is the situation we're now in. And remember, to use the induction hypothesis, we want to put ourselves in a situation where we have an injection from n, or from something at least, to m. Not m plus 1, but m. So the set consisting of these things. Now, here's something that would be nice. It would certainly be nice if the thing that led to m actually were n minus 1 if we just had a connection like that, right? So we know something leads to m because we're assuming we're in case 2 where m is in the range of f. So we know something leads to m, and we've given the name k, maybe to whatever it is that's leading to m. But suppose that the k were actually n minus 1. This is what leads to m. Then that is wonderful, because we could just take this portion of the diagram, delete that final edge there, and that would be an injection from a smaller number to m, right? And this would be a natural number, actually. If I take the numbers 0 through n minus 2, then that would be a natural number. And I could apply the induction hypothesis to this portion that I've boxed in red. So that would be great. However, I don't know that I have that, right? Chances are my k, the thing that gets mapped to m, is somewhere in the middle here. Chances are, right? And you might think, like, well, why not just take this portion of the picture and just delete that edge? So take this portion of the picture here. Okay, well, that doesn't really make sense because there could be, arrows. Well, actually, now that I think about it, I think it makes sense to take this portion of the picture. Yeah, there could be arrows like here going out to other parts there, but I think it makes sense to just delete all of the incoming arrows from here, or all of the outgoing arrows from here, and then leave only these edges in the picture. So then we'd be looking at a function, basically our original function f, but restricted to a smaller domain consisting of only those things from 0 up through k minus 1. And that should be fine. But the problem with that, I guess, is that even though it would put me in a situation where I can apply my induction hypothesis, it doesn't give me strong enough of a conclusion. So it would give me something like, so excuse the minus sign for now, it would give me something like k minus 1. So if I just focus on the red part, I think that would be an injection from, it would show that there's an injection from k to m, right? So then I would get k less than or equal to m using the induction hypothesis. But what I want is n less than or equal to m plus 1, right? And n could be much, much larger than k. So just knowing k is less than or equal to m tells me k plus 1 is less than or equal to m plus 1. But k plus 1, like n might be much, much larger than that. Okay, so what I'm trying to get at, sorry for the sidetrack there. That's me getting confused for a moment about why we don't just make this proof easier and just restrict down to this portion of the picture. And the reason is that while you can apply the induction hypothesis to this portion of the picture, it does not give you a strong enough conclusion. Eventually we want n less than or equal to m plus 1. All right, so another idea is to only delete this green edge from the picture and keep all other green edges. So only delete this one. So you would be keeping sort of like every other part of the picture other than this. So you'd be keeping like all this red stuff here. But then the induction hypothesis cannot be used because the function you're left over with does not have a natural number for its domain, right? Like if the domain consists of 0 up through k minus 1, and then k plus 1 up through n minus 1, skipping k, well, then that's not a natural number. That's just not what natural numbers look like. We'll have trouble, in the end, we'll end up having trouble using the induction hypothesis. This applies to natural numbers being used as the domain of an injection. So what to do then? This is where our earlier plan of digging into f and then trying to rewire and do a swap comes in. So we're going to try to get ourselves into the situation where actually this is what's connecting over there rather than something random in the middle. So the way I described this earlier when we were looking at an example in the previous lecture is I said cut here, right? And then, this one goes somewhere, I don't know where, but cut here also, and then swap them before sending them along their way, right? And that was like a modification we were making to the function. Now if I make that modification, it's no longer this function f. So how do I actually put this into my argument? Well, what I'm doing is I'm doing a swap before I do f. This is called precomposition, when you do something before you do a function. So I'm precomposing f by a swap. So a better way to look at it actually is, if I can make a bit of space there, is that first I'm taking this set n and carrying out a swap. So I'm going to create another function, but this one, I'm going to box it in blue, but it's not going to be a mystery box. I'm going to understand this one completely. All this one does is it sends it'll send k down to there and n minus 1 up to k. So it'll carry out the swap. So basically first swap them and then do f. And this function we can construct ourselves. Like you could just send, you could fix everybody, right? Just fix everybody in sight, everybody in between, just fix everything, except also carry out this swap. So don't fix k, don't fix n minus 1. Instead, let me emphasize that. That part of it. So the reason to fix everybody else here is to ensure that what you're doing here is actually a bijection. If this is a bijection, or at least an injection, then when you compose it, so you do this function, let's call it g. When you do g then f, so f composed with g, if both are injections, then the result is an injection. But look at what we have for the composite f composed with g. It sends n minus 1, and then follow, 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 up to k, and then back down to m. So you see f composed with g is exactly something that has that good picture where n minus 1 is going to m, right? Here n minus 1 is going to m. So to summarize, what we had originally was just this picture with f and some k going to m, right? And we thought it would be awesome if that k were actually n minus 1, if it were n minus 1 going to m, because then we can focus on just this part and apply the induction hypothesis. We don't necessarily have that, but we can precompose by another function, g, such that we do end up, when we look at the composite, we still have an injection, and we do end up having n starting here, ending up here, along the composite. So let's try to write up this idea and finish the proof.